All right, let's do some algebra. Let's take the unique irreducible representation of S5 of dimension 6. As in problem 1, I don't know if I'll upload that problem because it takes a while, and there's one step that I'm not 100% on. Yeah, basically if you just find the character table for S5, you could just Google it. There will be just one row that has a character of dimension 6, and you'll know which one that is because it's the character where you evaluate at the trivial element and you get 6, or evaluate at the identity, whatever. So now we're going to take this as a subgroup of S5, and we'll think of it as the permutations which preserve this decomposition. So a permutation of 1 through 3 times a permutation of 4 and 5. And so we get a representation of S3 times S2 by restricting the representation V from S5 to S3 times S2. And so this is obviously going to be a product of irreducible representations, and they want us to find what those irreducible representations are. All right, so first, we want to find the character table for S3 times S2. So, as in the previous problem, don't worry about that. Basically, what we're going to do is we're going to suppose that this, okay, so H is S3 times S2. Suppose that this restriction is written as a direct sum of irreducible representations with some multiplicities, mi. Now, we've done these before. We have character table. Let's see, I did not grammar well in this. I did not do a good grammar in this part. So we have this character table for S3 and this character table for S2. The one for S2, we know that for any permutation group we have the trivial one and the sign one. And in S2, we're thinking of S2 as a subgroup of here we're thinking of this as the permutations of the indices 4 and 5. And there's only two elements. We've got 1 and then we've got 4 and 5, and these are the only characters we have. As for S3, we know that we have the trivial character and we have the sign character. By the way, these are representative of conjugacy classes, and these are the number of elements in each. So we have the trivial and the sign, and then to get this final row, we need this column. If you sum the squares of the entries in this column, it needs to add up to the order of S3. So before we knew this was 2, if we just called it A, well, here we need 1 squared plus 1 squared plus whatever chi sub 3 of E is squared to equal, well, what's the size of S3? That's 3 factorial, which is 6. And so that means that chi sub 3 of E squared is 4, which means that chi sub 3 of E is 2. And this 3, there's nothing special about this 3. It's just the third character in this table. So anyways, this gives us 2. And once we know this, we can figure out the other ones by orthogonality. 1 times 1 is 1, and 1 times -1 is -1. So if we take the the dot product sort of this column and this column, we need 2 times whatever goes here to equal 0, which means that this has to be equal to 0. Similarly, this times this is 1, this times this is 1, and this times this. So we need this to be such that when you multiply these two things together, you get -2, and the only thing that does that is -1. So that's how you get this table. Anyways, okay, so we have S3 and S2. So how do we use this to get the character table for H? So here's what we're going to do. We're going to prove that it's basically we're going to consider the character table of S3 sort of the tensor product of that with the character table for S2 in some sense. But let's be specific about that. So now we're going to let G and H be arbitrary subgroups. Again, sorry for the abuse of notation here because we used H to refer to S3 times S2, but here we're using H to be just any group. So rho G is a representation of G, and rho H is a representation of H. Then we know that we can define the tensor product. We can define the tensor product of these representations as follows. And then what happens is if we evaluate this at G1, G2, H1, H2, then this is this. And so this is indeed a representation. So just in case you didn't trust me that this works. Well, wait, I guess you shouldn't have trusted me, because even though like we've talked about how to take the tensor products of two representations of the same group, but we have not talked about the tensor product of two representations, each of which acts on a different group, or each of which is a representation of a different group. So this calculation just confirms that we can actually do that. And then also we want the character multiplicity to be the same. We want the character of the tensor product of the representations to be the product of the characters, and we just need to do this calculation to do that, but it's really straightforward. All right, and then what happens if you do this thing? If you take the character of V1 tensor V2 with V1 tensor W1 with V2 tensor W2, then we just do a whole bunch of computations. This, we have the set G times H, which is going to have size G times H, and we can write this like this, and then it just becomes a product here. And so what this formula tells us, that if V is irreducible, if V and W are irreducible representations, then this inner product is, well, it's going to be it's going to be chi V, the inner product of chi V with chi V times the inner product of chi W with chi W. But since V and W are irreducible, the first inner product is 1 and the second inner product is 1, so you're multiplying them together. So the point here is that the tensor product of irreducible representations of G and H respectively is irreducible. So now we can find the character table for our original thing that we were calling H. What we do is we know that the conjugacy classes are just the direct products of conjugacy classes of the groups by themselves. We've got 1, 1, 2, and 1, 2, 3 for S3, and then we've got 1 and 4, 5 for S2. So we've got 6 of these, and then we had 3 irreducible characters for S3 and 2 irreducible characters for S2, and because of this formula up here, we know that we can obtain 6 irreducible representations of H by taking tensor products of the irreducible representations of S3 and S2. But if we do that, we get 6 distinct characters, and we know that there's 6 conjugacy classes, and therefore these are all of the irreducible characters of H. Okay, so that's good. So let's label them chi1 through chi6, just because I don't want to have to rewrite all of these again, or I guess retech, whatever. And we're going to call the corresponding vector spaces W1 through W6. So let's determine this restricted thing by evaluating this character on the conjugacy classes of S5. So basically we know that this, what's happening here is, so V is a representation of S5. And so what we can do is, if we want to figure out what the restricted representation is, we just take what we're basically just taking the character and restricting it to the conjugacy classes that correspond to things that are in H, because H is a subgroup of S5. So let's see here. If you look at the character table for this character for S5, let's see here. Does it? No, I don't go through and show it here. Yeah, let me scroll up way back to the beginning of this exercise set. Okay, so here, this is where it's coming from. It's coming from this, which I called chi7 in this problem. It's 6, 0, negative 2, 0, 0, 0, 1. Right, because remember, this was the unique representation of dimension 6, and if you look at this column, you see that this is the only one that has a 6 here, so it's the only one that has dimension 6. Anyways, so this is, an element of here would be like the trivial representation. Here, of course, like 1 to the 5, that means some, this is written using like a sort of, what is it called? It's like a partition notation. So here, 2 comma 1 to the 3 means that it contains, these are elements which contain a 2 cycle, and then they fix 3 elements. So it would be something like 1, 2. And similarly here, 3 and 2, this means this is a 3 cycle and a 2 cycle. Alright, so let's look at this and see which of these conjugacy classes could appear in S3 times S2. Certainly this one could appear. This one could appear. This one could appear. You could have a 2 cycle that's contained in S3 and a 2 cycle contained in S2. This one could appear. This one could not, because this permutes 4 indices, and so it's not going to preserve the decomposition 1, 2, 3, and then 4, 5. It's going to take either 4 or 5 are going to get sent to something in the set 1, 2, 3, which is not allowed in S3 times S2. Similarly, this is not going to come over either, because for the same reason, it will permute either 4 or 5 will be sent to either 1 or 2 or 3, and that's not allowed. So basically, we're going to bring this character over, but we're going to remove these rows. So it's going to be, all we're going to have is 6, 0, negative 2, 0, 0. Except, I think, let's see here, it's got to be the case. One of these is going to break into 2 things. Right, this is going to break into 2 things, because we see that this 2 cycle here, this could either, you could permute one of the elements, you could either permute 2 of the elements in 1, 2, 3, or you could permute 2 of the, not elements, but indices. You could, so you could have things like 1 and 2, which permute indices that are in 1 through 3, or you can permute 4 and 5, which is, of course, and we think of this in S3, and we think of this in S2. And so when we restrict it, this breaks up into 2 separate conjugacy classes. But the main thing to keep in mind in this problem when we do the restriction is that, let's see here, so we're going to get a bunch of zeros, and then we're going to get, the 6 is going to stay with the trivial one, and negative 2 is going to stay with 2 squared. So this is going to be things of the form like 1, 2, 4, 5. Alright, so let's bring these into our restricted character thing and figure it out. So see, that's exactly what we've done here. For the trivial one, which contains just 1 times 1, we get 6. For the one consisting of 2 distinct 2 cycles, one of them has to be in S3, the other one has to be in S2, and this gives us -2. And then all the other ones are going to be 0. Alright, so now we know all the irreducible characters, and we know the character that we are trying to break into a direct sum of irreducibles. So now we can just take inner products to figure out which ones of these are contained in this. Basically, if you, we know that the multiplicity of an irreducible representation in, okay, so let's introduce some notation to make it easier to explain. So let chi0 be this restricted character. We know that as evaluating it at the trivial element gives us 6, so its dimension is 6. So the dimensions of the irreducible subrepresentations must add up to 6. So now we need to compute the multiplicities of W1 through W6 in this restricted thing. And when we do these, so basically what we're using is that if we take chi0, chi-I, this is going to be I between 1 and 7. This is going to be the multiplicity of the sub. This is going to be the multiplicity of the irreducible representation I in chi0, or the multiplicity of the irreducible subrepresentation subrepresentation rho I in this the restriction from HS5 of V. All right, so let's do that. Basically, we do the same computation that we usually use, but we're going to ignore all the conjugacy classes that evaluate to 0. So here we want to take this inner product, so it's 1 over the order of the group, the sum over all things in the group, chi0 sigma inverse, chi3 of sigma. And chi0 sigma inverse, in this particular example, the inverse image of a particular cycle type is going to have the same cycle type as what you're taking the inverse of, and therefore we can just think of this as chi0 evaluated at sigma. We don't have to worry about inverses. So with that in mind, take 1 over 12, and then, so what are we going to do? This is chi3 we're evaluating at, so it's this one, this particular row. So we're taking this one and this one. So for every element in this conjugacy class, we're going to take this times this. So it's 1 times 2 times 6, and that's exactly what we have here. Similarly, for everyone in here, in this conjugacy class, there's 3 of them, and for each of those, we're adding 0 times 0, so it's 3 times 0 times 0, that's going to be 0. Here, we're going to have 2 times negative 1 times 0, but that's just 0. Here, we're going to have 1, 2, 0, that's 0. Here, we're going to have, 0. Well, 3 times 0 times negative 2, so that's going to end up being 0, 2. 0 as well, I should say. And then this one's going to be 0. So this is going to give us 12 over 12, which is 1. So, therefore, let's see, what did I call these? Did I call these W1 through W6? So, therefore, W3 is an irreducible subrepresentation of V. But we know that if we look at chi3 and chi6, so 3, 4, 5, 6, these two rows are exactly the same except on, let's see here, this column and this column. But what happens in these two columns? We look down here and we have a 0 here, and for this column we have a 0 here. So the calculation is going to be the calculation of the inner product of this row with this row in the table with this row in the table is going to be the exact same computation we did before, and we're going to get 12 over 12, which is 1. No. Right. So this and they agree, so then this inner product is 1 as well. Alright, so that's good. So we found two, so W3 and W6 are both irreducible subrepresentations of V. So now let's take the inner product with chi2, and we basically just look at it. Here, I won't draw these arrows anymore. But if we look at the second row, we get 1 times 1 times 6, 0, 0, 0, 3 times negative 1 times negative 2, and then 0. So we add that up, and we get 12 over 12, which is 1. And so then W2 is an irreducible subrepresentation, and of course this is multiplicity 1. And then again we look at chi2 and chi4, so the second row and the fourth row, they disagree here, and here, and here. So this one, and this one. And if we look at these three columns, we've got 0 here, 0 here, and 0 here. So the computation is going to be the exact same. And so then we're going to conclude that W4 is also an irreducible subrepresentation. All right. So this restricted this restricted character contains, so this should be, this restricted representation contains one copy of the representation W2, W3, W4, and W6. I guess I should have written either chi V contains one copy of chi2, chi3, chi4, chi6, or I should have removed the chi here and kept these as W's. It doesn't matter. The main idea is that this thing contains one copy of each of these. But now if we look at the dimensions of these, we've got 1, 1, and then we had 2 and 2. And we add those up, we get 6. But that's the dimension of this restricted. Again, this should be the dimension of the restricted representation. Therefore, this restricted... I made this issue a lot of times. This restricted representation is the direct sum of these. Therefore, well, wait a minute, what's the problem statement? Yeah, even the problem statement has it as the restricted thing of v. So I just made typos all throughout here, but the idea of the proofs is correct. I just could have written it more clearly. So anyways, we have this direct sum, and so we've written this restricted representation as a direct sum of irreducible representations of H. And that's exactly what we wanted to do in this problem. And so now we are done with the proof.